Hello and welcome to this video where today we're looking at how to determine the charge on an electron. So in the last couple of videos we've looked at how scientists developed the idea of the electron by looking at cathode rays, and then from that they were able to measure the specific charge by using electric and magnetic fields. So once they'd got the specific charge, what they really wanted to know was, because the specific charge was the biggest specific charge that they'd seen, they wanted to know whether this particle either had a really small mass or whether it had a really big charge. And also, if they could measure either the charge or the mass, then using the specific charge, they could then work out the value of the other one. So if they knew the charge, for example, they could work out the mass. So a guy called Milikan and his student did this. And from the exam board's point of view, what we really need to look at is we need to look at this. So we need to know what forces act on an oil droplet. So we're going to be working with oil droplets that, as we'll see in a bit, are put between two metal plates, and then we put a potential difference across these plates, and we can basically alter the motion of oil droplets. And we need to have a look at what forces act on these oil droplets. Once we know that, we can then actually find, using a variety of different techniques, we can work out the mass of the oil droplet. We can then use that to then calculate the charge on the droplet, and then in the end we need to say basically why calculating the charge on oil droplets led to the idea of the charge on the electron. So Millikan's experiment basically looks like this. So what this shows you is it shows you this thing here is called an atomizer, which sounds a very fancy thing. So we'll label that. So that's our atomizer. And basically all it is this thing here is full of oil, and you squirt the oil through a tube into here. So you get really small droplets of oil, so they're incredibly small. And as they travel along here, because they rub along the sides of this thing, then they get, by friction, they get charged up. So each of these oil droplets is now charged. So the scientists knew that when you charge these up, it was basically the same as firing cathode rays onto them. So they collected the same particles that were basically being transmitted by the cathode rays. So if we can find the charge of the things that are on here, then we can find out the charge of the cathode rays or the electrons. So you squirt your oil through here, it basically becomes incredibly small droplets, and they gradually, very slowly fall down here. Now, what we don't want is this second chamber below. So there's one chamber on top, there's a second chamber below. We don't want all of the droplets falling down here, because otherwise we'll not be able to see what's going on. So we put here a little tiny pinhole. So it's a really small hole. It's called a pinhole, like that. And so only a few of these will actually fall down here. And so we'll be able to concentrate on just looking at these ones. Now they're incredibly small, these things, so we need to be able to see them. So this thing here is a microscope. And that simply allows us to actually see the oil particles. Now the microscope was made so that it had a scale inside it. So for example, there would be a scale like this, so we can measure distances. And so as the oil droplet gradually fell down here very slowly, because it was only small, we could time how long it took to move a certain distance, and from that you can work out speeds. So once you've got these oil droplets falling down, what Millikan thought, and what was like the real key part of this, is because these are charged, you can manipulate them with electric fields. So what he did is he put a variable power supply here, so he could change the potential difference between here and here, because these are just two metal plates, and so he could charge these metal plates up. So once these small charged bits of oil were in here, they'd be subject to an electric field, and so they would feel an electric force from the electric field as well. So that was his basic setup, and so he squirted this oil in, it gradually fell down here, some of it went through this pinhole and it fell down, and then he was able to manipulate this and move it up, move some of the oil particles up or downwards, or actually hold them stationary, simply using an electric field, and he did that by changing the potential difference between these two things here. So if this was a negatively charged particle, if you made the top plate positive and the bottom plate negative, then you basically could make this thing just hover, because its weight would be pulling it downwards, and the electric force would be basically pulling it back upwards, and those two forces would balance. So that's the setup. in order to calculate the charge, we have to do something else first. So what we really need to do is find the mass of a particle, as we'll see in a bit. And in order to find the mass, what we really want to do is we want to find the radius of an oil droplet, because once we know the radius, then what we can do is, because we know that the mass is equal to the density of something times the volume of it, and if we assume this thing is spherical, then the volume is equal to 4/3 pi r cubed, like that. So if we can find the radius, we can find the volume of the oil droplet. If we can find the volume of it, then if we know the density of it, we can find the mass of it. And then, as we'll see in the next section, if we can find the mass, we can then find, basically, we can find the charge that's on this thing. So the trick to this is basically to allow this thing to fall at terminal velocity. So if you remember from GCSE and also from also from your mechanics studies last year, what if something falls at terminal velocity? When it first starts falling, the only force acting on it is its weight downwards. As it falls faster, the size of the weight remains the constant value, but there's a drag force upwards, so F, and we'll put a little D on it to show there's a drag force. And as it gets faster and faster, then eventually what happens is, because the weight stays the same but the drag force gets bigger, eventually these two forces balance out and the resultant force becomes zero. So it doesn't accelerate anymore, and so therefore it falls at a constant velocity. So that's what Milikan looked for. And he basically said, okay, so I've got these very small droplets and the weight is downwards like this. Now, because it's falling through a fluid, and air is a fluid, then at the time, and even now, we know that the drag force in the fluid is given by something called Stokes' law, and that basically is equal to this. So it's equal to 6 times pi times this eta symbol times by r, and then times by v. So that looks quite complicated. Obviously 6 and pi are just numbers. This eta thing is the viscosity of air. So viscosity. So that's a viscosity of the fluid that the thing is falling through, and in this case it's air. So, and that's measured in Pascal seconds. R is the radius of our oil droplet, and V is the velocity. So that's our velocity, and velocity is measured in meters per second, and the radius is simply measured in meters. So because this is falling at terminal velocity, what we can say is that the force downwards is equal to the force upwards. So in other words, mg is equal to our 6 pi, we'll get rid of that, 6 pi eta rv, like that. So we've got this particular equation here. Now what we're going to do is we're also then going to use this equation here and kind of put these two things together, because we know that mass is density times volume. Volume is given by this thing, and so we can take this. So if we put these two things together here, we've got mass is equal to the volume times the density. So if we put this as 4/3 pi r cubed, so that's a volume multiplied by the density. So that's the mass, and the mass we can put in, and we can take this equation and put it over here. So if we put this equation and this equation together, we get that you get 4/3 pi r cubed, 4/3 pi r cubed times the density, that's your mass, multiplied by g gives you the weight, and that's equal to 6 pi eta rv. So, and then we can change it. We can basically rearrange this and just make r the subject. So what I'm going to do is, if we do all of the maths in the end, what we end up with is that r squared is equal to 9/2 multiplied by eta v over the density and acceleration due to gravity. So, but with Milikan doing his experiment, he could work out that the radius simply by measuring the velocity, because The viscosity of air is you can basically measure that. That's fairly straightforward to measure. The density of your oil that you're using is easy to measure. This is just 9.81, the acceleration due to gravity. So if you can measure the velocity, then you can measure the radius. And once you've worked out the radius, you can then basically take it and you can plug it back into here, and you can work out the mass. So if we do this, in the end, this is the thing that we really want to work out. And the way we do it is by using this equation here to find the radius. And once we've got the radius, we put it back into here to find the mass. So we've got the mass of this object, and so we know that this mass is falling down. So what Milikan then did is he said, okay, right, these things are charged, and so what I'm now going to do is I'm going to now switch my power supply on, and I'm going to basically make, if these things are negative, I'm going to make this thing a positive thing. So what I'm going to do is basically hold my thing stationary. So it changes this potential difference, and so this oil droplet now basically stays still. So in terms of the forces acting on it, you've got the weight downwards, and we know mass, and we know the gravitational field strength, and we've got our electric force Fe upwards. And that's simply equal to the charge on our particle. So let's not call it E, let's call it Q. So that's the charge on the oil droplet multiplied by the electric field strength between the plates. And we know that electric field strength is just equal to, for two parallel plates, is just equal to the potential difference between them divided by the distance between them. So actually the force is equal to Q V over D. So the force is proportional to the potential difference. So we know that these two things are equal to each other because we've balanced the forces by very finely tuning this until the oil droplet basically stops. So we know that mg is equal to the charge of our oil droplet times the potential difference over d. And so the v we've measured, d we can measure because that's simply the distance between the plates. G is the acceleration due to gravity. M is the mass that we were able to find out by looking at the terminal velocity when it was moving down. Now it's stationary. This equation is right. So from this we can work out Q. So Q is equal to simply mg d over v. And so once we've done that, we can work out the charge on our oil droplets. And so just to reiterate, what we do in order to find the charge of our oil droplet is we simply take all of this. So we start off by calculating the radius of our oil droplet by looking at Stokes's law. So that's this thing here. We then, once we've found the radius, we can then put it back into here and we can find the mass of our object. Once we've done that, we then turn on our power supply. We stop the object from moving altogether so that the weight and the force on the electric field are balanced. And so we know this equation here, and so we can calculate the charge on this object simply by multiplying the mass that we work out from finding the radius, multiplied by the acceleration due to gravity, and the distance between these two plates here, and then we divide that by the potential difference of this particular power supply. So we're going to have a look at this really quick worked example. So what we're told in this question is we have an oil droplet. The oil has a density of 980 kilograms per cubic meter. A droplet of oil is falling vertically down through the air, and it's moving at a constant speed of this value here at 1.5 times 10 to the minus 3 meters per second. The viscosity of the air that the oil is falling through is 1.8 times 10 to the minus 5 Pascal seconds, and the acceleration due to gravity has our normal value of 9.81 meters per second squared. We want to calculate the radius of the oil droplet. So as we've just seen, the radius squared from our Stokes law equation is equal to 9 multiplied by, well, we'll leave the multiply sign out, 9 multiplied by the viscosity of the air multiplied by the velocity that the oil droplet falls at, divided by 2 times the acceleration due to gravity multiplied by the density of the oil itself. So if we put our numbers into here, then we've got 9 multiplied by, well, the viscosity is this number here, so it's 1.8 times 10 to the minus 5 pascals, multiplied by the velocity it's moving at, which is 1.5 times 10 to the minus 3 meters per second, and we divide all of that by 2 multiplied by the acceleration due to gravity, 9.81, multiplied by the density of the oil. The density of the oil is 980 kilograms per cubic meter. And if we put all of that into our calculator, we end up with 1.263 times 10 to the power of minus 11. And if we wanted a unit for this thing, this is a radius squared. So radius is measured in meters, so radius squared is measured in meters squared. Now we don't want that, we want to find the radius. So if we just square root the answer that we've got, our radius therefore is equal to the square root of 1.263 times 10 to the minus 11. We do that on our calculator, we end up with 3.555 times 10 to the power of minus 6 meters. Now if we're going to be properly accurate about this, this number is to two significant figures, so is this one, so is this one, this is to 3, so we should really give our answer to the smallest number of significant figures in the question, so therefore our answer, finally, 3.6 times 10 to the power of minus 6 meters, and we underline it to show the examiner what our final answer is. So that's the first part of the question. Our second part of the question is we're given exactly the same amount of information, so the oil is still at the same density, it was falling at the same speed, etc. But now the electric field is turned on and our oil droplet is held stationary when we change the potential difference between the plates to be 1800 volts. And the two plates that the oil droplet is held between are separated by 1 centimetre. We want to find the charge on the oil droplet. So if we think about what's going on, what we've got is our oil droplet is there. The forces that act on it are its weight downwards, and there must be a force upwards because it's stationary. And this force is the force from the electric field, which is the charge multiplied by the electric field. And as we've just seen, this is a uniform electric field, and so the electric field strength is given by electric field strength is the potential difference divided by the distance between the plates. Now, as we know, if this is stationary, the resultant force is equal to 0. So in other words, mg is equal to this particular force here. So in other words, mg equals the charge of the oil droplet multiplied by the potential difference between the plates divided by the distance between the plates. And if we rearrange this, we get that the charge of our oil droplet is equal to the mass of the droplet multiplied by the acceleration due to gravity multiplied by the distance between the plates, all divided by the potential difference between the plates. So if we look in the question, the potential difference we know because it's 1800 volts. The distance we know because it's 1 centimetre. Acceleration due to gravity we know from our data sheet. What we don't know is the mass, but we do know the radius. This is the same radius that we've just worked out earlier on. So if we do this little calculation over here, the mass, because density is mass over volume, mass is equal to the volume multiplied by the density. If we assume that this thing is a sphere, the volume is given by 4/3 pi r cubed, and then multiplied by the density altogether to find the mass. So if we take this and we put our numbers in, we'll go down here, the mass is equal to 4/3 times pi times the radius, which was 3.555 times 10 to the power of minus 6 cubed, multiplied by the density of the oil. The density is the same oil as before, so the density is 980. And if we work that out on our calculator, we get a mass of 5.83 times 10 to the power of minus 15 kilograms. So now we do know what the mass is. So we've got all of the information we need to work out this charge. So if we go down here, the charge of our oil droplet is equal to the mass, the thing we've just worked out, 5.83 times 10 to the power of minus 15, multiplied by the acceleration due to gravity, 9.81, multiplied by the distance between the plates. Now it's given in centimetres, we need it in metres, so that would be 0.01 metres. And then we divide it by the potential difference, 1800 volts. Again, if we do that on our calculator, we end up with 3.2 times 10 to the power of minus 19 coulombs. Underline it, show the examiner it's our final answer. So what we've actually found by doing these two calculations is that the charge on the oil droplet is given by this many number of coulombs. So you might be wondering why this is important. Well, Milikan did this a lot. He did this over and over and over and looked at lots and lots of oil droplets. What he found that was no matter what he did, every single time the charge on the oil droplets was always a multiple of this. Every single time. He never ever saw a charge that was less than this, and he never ever saw charges that were fractions of this. So, for example, you can't have like one. He found that you can't have 1.5 lots of 1.6 times 10 to the minus 19. They were always whole numbers of that. So what he really found is that the things that are charging these up, the particles that are going onto here, must have a charge of this, because if you've got just one particle, your oil droplet will have that charge. Two of these particles, you'll have twice that charge, and so on. So what Milikan had really discovered, he'd actually found that the charge on the electron was given by this. And that enabled people then to say, right, okay, so we know the specific charge of the electron, we now know the charge of the electron, we can therefore work out the mass. And that's where they came up with the mass of 9.11 times 10 to the minus 31 kilograms from. So this was an incredibly important experiment. And so going back to what you need to be able to do, we need to be able to look at the forces that act on these oil droplets in terms of Stokes's law for the drag force, and also the weight, and also the electric force from the electric field. Know how to find the mass of the droplet, and that came from the radius. So once we found the radius and we know the density, then we could find out the mass. Once we found the mass, it was then really quite straightforward to find the charge, and then you simply have to know and be able to explain why it is that this was a really, really important experiment. So that was the third video in Turning Points, and we've just had a look to see how Milikan found the charge on the electron. So thank you very much for watching, and I'll see you again soon.